Hello student. Today we will discuss about work energy power part 3. Myself DC Bhatt, PGT Physics, Kendriya Vidyalaya, OF Muradnagar. Today we will start it from potential energy. Now what is potential energy? The energy possessed by body by virtue of its position, by virtue of its position or configuration or deformation is called potential energy. Like gravitational potential energy. Consider a body of mass m is lying on the surface of Earth, as in this figure I am shadowing. This is the body which having mass m. So what will happen here? The gravitational force on the body is mg, and it is vertically downward. This is weight and it is mg, and it is vertically downward. To lift the body up with a constant velocity, with a constant velocity, that is, there is no acceleration, we require the upward force mg. We require the upward force mg. If we lift this one with a height h, the work done by force will be W is equal to force into displacement. Displacement is h. The force is vertically up. The height is vertically up. So the angle between them is 0. So the work done to lift the object for a height h, we will have the work done as equal to mg. Right? So it will be mgh, that is gravitational force. Now next is the spring. Here we have an string. This is a string. And the mass of this string is negligible. It is attached with a rigid support. This is rigid support. And the other end is free. This is free end. And this is rigid. That is, the end is fixed, because here it is rigid support. When no force is applied to the free end, there is no force at this point. It is in equilibrium position. The spring has its natural length. This spring has natural length. Now what will happen if there is a force applied? If there is a force applied, here we are applying the force, the spring will start to stretch, and this stretches up to the length x. Now it is found that this stretched spring has the length directly proportional to the applied force. So the spring gets a force that is called force of elasticity here. It is Fs, and the hand applied the force F to extend the length x. Then the increase of length, and if we compress, the length will decrease. The increase or decrease in the length of the spring is directly proportional to the applied force, which is known as Hooke's law. In this figure, the displacement or extension of the spring, its equilibrium position is x. This is extension. Right? Then the applied force is directly proportional to this extension. The applied force is directly proportional to this extension. And this law is called Hooke's law of elasticity. And if we remove the proportionality sign, we will use a constant. Here is the constant, and the constant is K. The spring also exerts the force on equilibrium, that is spring force, and it is equal to now minus Kx, because it is opposite to the force which hand is applying. This K is called the spring constant or force constant. K is called spring constant. It is property of that spring, or it is also known as force constant. Because it is property of the spring, its value is different for different type of spring. Its value is different for different type of spring. The restoring force, because the spring force is restoring, the restoring force per unit extension is called spring constant. And the value of spring constant K is F by X. Its unit is Newton per meter. So these are the basic points which we have to know about the spring and the Hooke's law. Now next point is the potential energy of the spring. Here we have a graph between the displacement x and the applied force F, and the restoring force is just opposite and equal to this F. And remember, K is spring constant. The elastic potential energy of a T-storied spring depend upon its shape, how much it is compressed or stretched. According to the Hooke's law, F is equal to Kx. So total work done, W, by the force in increasing or extending the spring from 0 length to x length. Here, we are writing the x is equal to 0. That is, displacement is 0 as there is no external force applied. And when force F is applied on this one, the extension comes about x. So there will be a work done to increase the length from 0 to x. The work done will be represented as the line integration of force from length x is equal to 0 to x is equal to x. So in place of force, we may write here kx, which is the Hooke's law. K is a spring constant and it is property of the spring, so we will take out from the integration. So integrating the value of x, we will have x to the power 1 plus 1 upon 1 plus 1. From the formula, x to the power n dx is equal to x to the power n plus 1 upon n plus 1. So here n is equal to 1, so it is 1 plus 1 upon 1 plus 1. And the limit are from 0 to x. So we will use the limit. First we will use higher limit and then lower limit in place of x. So we will get w is equal to kx squared by 2 minus 0 squared by 2. So it is half kx squared. This work done by the force in increasing the spring from extension 0 to x. So the spring itself now capable to doing this amount of work done when the stressed force is removed. When the force of the external force which is stretching the spring is removed, then this amount of work done, that is half kx squared, is capable to do work by the spring. Therefore, we say this amount of work, that is half kx squared, is stored inside the spring. And that's why we say this work done is the potential energy of a spring. And it is represented by U. So U is equal to half kx squared. That is the potential energy of the spring. After that, we will use some small points of interest. The first one is the power. You already know the power from class 9th. The rate of doing work by a body with respect to time is called power. And power is represented by P, and it is work by time. And the unit of power is joule per second, and it is also known as watt in SI system. The average power, it is defined as the ratio of total work done by the body to total time taken. So if power is different in different time, the work done is different in different time, so we will have to find the average power. And the average power is the total work done upon total time. That is sigma W by sigma T. Here delta T is time and work done is delta W. So it is total work done upon total time. The second point of power is the instantaneous power. The power developed within the body at any particular instant. At any particular instant of time is called instantaneous power. Or the average power evaluated for short duration of time is known as instantaneous power. As the word instant is showing, for a very short duration, it means the time is very, very small. And this time is very, very small and it is represented by delta t. And it is tending to zero because the time duration is very small. So we will use P instantaneous, that is instantaneous power, is equal to limit. The time duration is very, very small, that is delta t is tending to zero, of P average. Or we may write the value of P average as sigma delta W by sigma delta T. Now, second point of interest in this chapter is conservative forces. Let us consider here a force which is applied on an object and produce some work. If the force which create the work in moving an object against the force is independent of path followed. It means if we have an object and we are applying a force on this one, the object start to move. It means it is doing work because there is displacement as well as force in that direction. So when the object is moving from any point A to B from a different path and the work done comes the same, then we say this force is conservative in nature. For example, here we have a mass m, and this mass m is changed from position A to position B by various paths. The first path is, first we travel horizontal, then vertical, and reach at point B. Second is, first we start vertical, then horizontal, then we reach at point B. And the third possibility is when the object starts from A and we reach at point B from path 3. If the work done is same in all the condition, whether we take path 1 or we take path 2 or we take path 3, if work done is same, then we say the force applied on this object for displacing from A to B is called conservative. Forces are said to be conservative in nature if work done against the force get conserved in the body in form of potential energy. So we also say forces are said to be conservative in nature if work done against the force get conserved in the body in form of potential energy. And remember, it is path independent when we displace from one point to another. It depends on only the mass of object. The conservative force, when applied, the work done depends on mass of the object and initial and final position of the object. Such type of force, when work done is path independent, are called conservative force, and example are gravitational force, elastic force, electric force, magnetic force, and all central force are conservative in nature. So we may consider property of conservative forces. Number one, work done against these forces is conserved and get stored in the body in form of potential energy. Second, work done against these forces is never dissipated. Never dissipated. It means it remained constant, whether the path followed. It never dissipated by being converted into non-usable form of energy like heat, light, and sound. So work done against these forces, that is conservative force, is never dissipated in form of heat, light, sound, etc. And third, work done against the conservative force is a state function. State function means not path function. They are path independent. They are path independent. Then work done against conservative force is a state function. They are path independent. Work done against conservative force is zero in a complete cycle. This is again an important point. If we say the object starts from point A to point B, there is work done. And if the object comes again from A to B to A, and it forms a cycle, then what happens when the work done from A to B and work done from B to A for complete cycle will be zero. It means work done from A to B and work done from B to A for conservative forces will be zero. Thank you. for watching this video. Hope you like it.